making the changes due to my schedule. I'm so sorry, but I will try my best to share something about gas chromatography today. So when we talk about gas chromatography, oh gosh, the important person that we usually remember is Professor Martin, is this Mr. Martin. So sorry, this is in Japanese. Just want to let you know that, well, I think I mentioned before when I mentioned the history of chromatography. So Martin is, he received a Nobel Prize in Chemistry in 1952 for the invention of partition chromatography. So if you recall the history slide I show in the first lecture, maybe. So Martin invented partition chromatography in 1941, and then paper chromatography, which is also the simplest, but yet the basic of the TLC right now. Thin layer chromatography is based on the paper chromatography, which is also introduced by Martin. And then in 1952, he also introduced gas chromatography. So, in all the chromatography, I mean, the retention mechanism is the same. Yeah. So this is also based on the partition. Yeah? So partition, and then just that the mobile phase is a gas instead of a liquid. Yeah? So and then after he introduced this gas chromatography, and then he also received a Nobel Prize for partition chromatography. Yeah? So anyway, Martin invented it, but another important person most people remember when you talk about GC is this Gole. So Gole column. So Gole column, when we talk about Gole columns, it means this is the column for open tubular, and this is the column for gas chromatography. You cannot be something else. So Gole column means GC. Yeah? So what is so important about this GC is for the past few weeks, we talk about the packing materials in liquid chromatography, the partitions, and then reverse phase, normal phase, and things like that. So the normal pack column means that everything is packed inside a tube. Yeah. So today I bring the tube, just in fact you want to see. So this is usually the tube we will use, and then this is the stainless steel, and then we will cut and we will pack inside. And then this Gole column means it is the open tubular column. Open tubular means the meter is blank. There's nothing. Yeah. So then how we make the column? We make the column by coating a liquid phase, something like not really a liquid phase, but it's like a wax, So we just coat in the inside of the capillary or inside. Usually when we say open tubular column, it must be a capillary. It cannot be something else like this. And actually today I also bring my capillary columns. So this is the capillary column. Yeah. So if you look at the size, it is so different. Yeah. So this is the size of the capillary, and this is the size of the pack column. I don't know if you can see. Anyway, maybe later after when I don't share the slide, maybe it will be bigger for you to see the columns. So the capillary for the Gole columns, it's a coating in the inner face of the capillary. I will explain more when I explain about the column. Yeah. So this Gole, he published a paper in 1957 saying that vapor phase chromatography and the telegrapher equation. So maybe you still remember I talked about important parameters in chromatography, how we have to improve the separations by improving the retention factors. So another important parameters is the Van Dimter equations. So Van Dimter equations tell us the informations of the maximum velocity of the mobile phase, and also the how good the column can be. So the plate number, the bigger the better, but in the Van Dimter, we use the plate height. Yeah. So plate height, it has to be the smaller the better. So if you look at this is the overall effect of Van Dimter. The lowest, the best separation plate here is here. So that means we have to use this mobile phase velocity, mean the speed of the mobile phase. Yeah. Okay, this is usually the equation we use for Van Dimter. So they are factor A, factor B, factor C. So caused by the multiple path if we have to pack the column. Yeah. So if you remember, when I talk about Gaulet columns, it is its open tubular. Yeah. So open tubular means there's no packing materials. Yeah. So when there's no packing materials means the multiple paths here, the additive divisions is near to zero. Yeah. Near to zero means that the separations of the GC has to be much better than the LC. So if you look at this is for the LC, yeah. So the smaller packing materials, the better. The lower you go, the better it is, yeah. So for GC, since there's no packing materials for the Gaulet column, so that is why when Gaulet introduced the column, he becomes so popular because the pack column like this, nobody will use the pack column anymore, yeah. But in some cases, when there's some separations of compounds that has very, how do you say, very small retention, we still need to use the pack column to increase the retention. Yeah. But in most of the case, if the sample is volatile, meaning that because we have to analyze in gas phase, so anything or any sample with the boiling point, I mean, which is volatile, that means can be vaporized, become a gas, can be analyzed in GC. So usually compared to LC, the molecular weight we usually can analyze in GC is around 1,000 or less than 1,000. So, okay, so this is one of the typical lab from this company. I just used this. It's from there are many analytical company in Japan that you can send samples and also you can and get your results. Sometimes very fast. Yeah, you just send the sample and they will do it for you. And sometimes in 1 week you can get your results. Yeah. So in my lab I have a very small GC, but not this is GCMS. Yeah. So if you look at this whole thing is a GCMS by a company called JMC. There are many small companies in Japan produces good GC I mean apparatus. But I think in Indonesia, maybe you buy from Shimadzu or maybe you buy from Agilent. Agilent, I think, is the world famous brand for GC because originally their biggest share is GC, Agilent. But Shimadzu is also having very good market right now. And another European company called Restec also, it's producing very good and reasonable. Yeah, the price is reasonable. And these companies, the one I have is Shimadzu, is very, very old Shimadzu GC. So it's a GC10 with only FID. I don't have a mass. I want to show you the mass spectrometry. So this is the GC is only here. This one is the mass spec, and this one is the auto sampler. Yeah? So usually in a company or in a usual lab like this, we don't use syringe like this. Usually we use syringe, but sometimes the auto sampler is something like this. So you just put the vial inside the auto sampler. So everything will run automatically. Yeah. But in our lab, usually we have to use syringe like this. So we just manually inject our sample one by one. So we inject one when we finish the analysis, and then we have to clean and we have to inject again. So for us, it's usually manual. Yeah, I mean when you do research, but in a company, usually they have this auto sampler. So and then usually it's automatic. Yeah? Okay, so to show the components of GC, I will use a simple FID detector here. So it is quite similar to LC. Yeah? You need something to pump the mobile phase, and then you need a sample injector, and then you need a separation column. And after separation column, you need a detector. Yeah. So FID detector stands for flame ionization detector. So it is very cheap. It's one of the cheapest and one of the I call it general detector. Yeah. As long as there's anything organic compounds, we can analyze with FID. And then for the gas, if you look at the here, instead of the liquid, in GC, of course, we use a gas as we call it. We don't call it mobile phase, we call it carrier gas. So carrier gas means the gas will carry the sample here. If you notice here, for GC, we must have an oven, yeah? And if you notice here, part of the injector have to be inside the oven, yeah? This is because when we inject the sample, the sample have to be volatile, yeah? So we have to volatile and make the sample to become a gas. In this way, it is easier when the carrier gas will come here. Yeah. So usually we use higher temperature. We use temperature program to program the temperature to have maximum separation. Yeah. So in LC, usually we use the combinations of the mobile phase like 70% acetonitrile or 30% water. We use a mixture. Yeah? But in GC, as you can see, there's only one gas. Yeah? So there's only one gas. So how do we want to increase or decrease the retention is by controlling the temperature. Yeah? So the temperature is very important in GC. And then sometimes some people forget, but usually the injection part here, usually we have to use higher temperature, yeah? Because if the temperature here is lower or it is not so good, sometimes your sample will be stuck here and you cannot get a good separation. And sometimes you will get some overlapping of samples here. And this have to be very careful if your sample is like a polymer or something. Yeah. So, but usually it is very typical to use GC to separate polymer, unless you have to have like a thermal analysis part. Yeah. So that is one of the recent development in GC. People are modifying the injection part. Yeah. So like when you have a different injection port, like when you use very high temperature or something, you can break down some polymer and you can also analyze in GC. Yeah? So this is one of the typical components. Carrier gas, sample injector have to be inside the column oven, then the column oven and the column, of course, then the separations, after the separation, the detector. And if you see the detector also, we need some gas. Yeah. So usually we use the combination of air and hydrogen here so that we can have, for FID, we use air and hydrogen both to get the maximum detection. Yeah. So this is one of the overview of GC analysis. So like I mentioned before, the sample have to be vaporized here, and then the carrier gas will carry the gas, the sample into the column. And by controlling the gas temperature and also using different column, we can have the separations and then it will be detected. Yeah. So the detection will be based on the electrical signal. So the bigger it is, the more, the more of the concentrations. So this is, I think the overview of GC, it's almost the same as LC. Yeah. Right. Okay. Right. Okay. Okay. From now, I will talk part by part. The important, I think I will, due to the time constraint, I will focus on the carrier gas, the columns, part of the column, not all the column because there are so many columns in GC. But I will just introduce the important ones and also the detectors. Yeah, detectors also, it's a lot. The common one is GCMS, yeah, but I will talk something else, not GCMS, because I think if you Google, everywhere is GCMS, so I will share something else. Okay, first about the carrier gas. The most important quality of the carrier gas, it must be an inert gas, yeah, the gas that do not interact with your sample. So basically, there are 4 types of carrier gas like this. So of course, the carrier gas having the diffusion rate is much faster than LC because it is a gas, not a liquid. And then depending on the detector, we have to choose different carrier gas, which do not interfere with the detection as well. Yeah. So the commonly used carrier gas is helium, nitrogen, hydrogen, and argon. Yeah. So, okay, just a simple question. From these 4 different gases, which one do you think is the best or most commonly used? I think maybe if you Google, maybe you know the answer. Yeah. Usually when I write something, the common one, I will write from the top to bottom. So helium is the most commonly commonly used. In my lab, I use nitrogen. Yeah. Of course, I also have helium line, but usually I use nitrogen because it is cheaper, it's safe and cheaper. Hydrogen is dangerous, so usually it's just helium or nitrogen. But helium is 3 times more expensive than nitrogen. So usually when right now I don't use GC because most of my students, we just use LC. So GC, sometimes when we have a good monolith column, we want to try for GC, then we will do GC, but very rare I will use GC. I just use capillary LC. So anyway, I will explain about why this helium and nitrogen is more common. The most, the best carrier gas is of course helium, but because it's expensive, yeah. So usually, depending on the price and the purity, yeah. If you can get 99.99% helium, then it's very expensive. But because of the productions of helium now is getting less, so now many company, they try to switch the use of carrier gas by modifying their detector and sometimes the column. And now maybe it is more common to use hydrogen, yeah? But still helium, it's one of the best separation with it's safe, yeah. It's safe and it have a wide optimum linear velocity range. Later I will show this optimum linear velocity, yeah. So another one, nitrogen, that I use a lot because it's very safe and the cost is reasonable, yeah. So helium is 3 times of nitrogen, yeah, depending also on the purity, yeah. And nitrogen, it's easier to get, yeah. And then, but the disadvantage is the optimum linear velocity is very narrow and it is very low, yeah. So what do I mean by the optimum linear velocity? If I would like to share this. So this is the plate height. So when the plate height lower means the separation is better, yeah. For nitrogen gas, so after, because of the molecular weight, so we cannot use very high velocity. Yeah? So when the velocity is more than 20, you can see the plate height will increase, meaning that the separation will become very bad. Yeah. So because of the molecular weight of nitrogen is different than helium. Yeah. So comparing helium and hydrogen, of course, if you look at both of them, this is what we say the wide range, yeah, wide range of optimum. Optimum linear means this is the linear velocity. It means that no matter how fast you use the gas, the speed of the gas, you can maintain the same separation efficiency. So meaning that when your sample, you want to do fast separation, you use a high velocity of the gas, but still you can maintain the separation. Yeah. So this is quite different in liquid chromatography. Yeah? So if you look at the gas here, helium and nitrogen, it is almost the same from 0 to almost 80. Yeah? It's crazy, yeah? Because this is so difficult to get in liquid chromatography. And for the nitrogen, it's close to, because of the molecular weight, so it's affected by the speed. And because of this, we cannot get a very good separation after 20 cm per second. So this is the velocity, means the speed of the gas. So meaning that when we want to choose a carrier gas, we have to consider the cost of the gas, whether it is safe or not. And of course, we need also to consider how much time we need for the analysis here. So when the separation is better, meaning that we can reduce the separation time. Yeah. So all right. So next, I would like to talk about the column. Sorry, carrier gas. Is there any question about carrier gas before I go to the column?
Yeah, please, everyone, students maybe want to ask Prof. Lim about the column, the carrier gas.
Yes.
I mean,
yeah. Anyway, I will continue until somebody have a question.
Sure.
Yeah,
Sure,
I
Prof.
think previously I was busy with the question and we have we overdue the time,
The
and
time,
then
yeah.
affected your next lecture. Yeah, I'm so sorry. Today I will keep my time. Yeah. So anyway,
Yeah.
okay. So I will come back to this slide. So if you look at here, the PET column is also used in LC and GC, but the open tubular, this is the Gauler column, is only used in GC. And actually the monolith column is considered the next generation column. I explained a bit in LC. Maybe in my webinar, I will explain more on this, how we make the ion exchange monolith column. So I will not do it here. So sometimes this monolith has the porosity between the particle packed column and the open tubular. Yeah? So we consider this monolith column can have better separation. Yeah, but so far the applications of monoliths, it's only in LC, because we still cannot achieve the liquid phase like Gauler column. So it's very difficult. Yeah, and the pressure of the column is still very high. Yeah? So I try to use very short column, I try to change many things, but still when we want to apply to the GC, it was difficult. Yeah, but somehow some people managed to do something by reducing the capillary size. If you have time, maybe you can Google on the internet. I mean the Web of Science. Then there's a group, and the research group in China also, they are progressing a lot. Yeah, so we really have to catch up with them. But anyway, so there are two main only two types of column used in GC, which is the packed column and the open tubular column. GC can all types of heat can be separated. How did it happen? All type of gas can be separated. Well, it depends on your compounds. Yeah, I mean, to separate the gas depends on the molecular weight of the gas. Yeah, so if the molecular weight if it is an organic compound and they have different molecular weights, and usually we can separate them. So later I will show some chromatogram, then maybe you can see how the separation is being done in the GC. I hope this answer your question, Vita. Anyway, so the packed column for GC, it's connected. This is inside the oven, the column oven. Yeah. So okay, thank you. Right. So when you open the column oven, it will be something like this. So this column, it's about, I think that one of these is about 1 meter usually. So usually we use 2 meter to separate. And the diameter, this diameter is 4 mm. The one I have here, this is almost 2, is 1.5 mm. This is 1.5, yeah. So it's smaller. So the length, it usually have to be more than 1 meter, yeah. So because GC and LC is different, and the diffusion of gas is different. That's why the separations, of course, the peaks is also so different for GC and LC. But in fact, the pack column now is very few, yeah. I mean, not many. I can say if you buy a new GC, usually they will give you this capillary column, yeah. So they will not give you pack column because nobody wants to use pack column now, yeah. So usually it's a capillary column like this. So for capillary columns, so this is it's a Gole column, so it's open tubular. So in the middle, it is a blank. So we just, it's a coating, yeah, coating of well, we call it liquid phase is because the it's like a wax, yeah. So it's something very it's like stick to the wall of the inner diameter of the column. And then the composition, actually most of the time it's the pore on that, it's very a lot. That's why we call it, usually it is called liquid phase here, because there will be some diffusion, and there will be, when the gas are here, it will be absorbed here, and that is where the separation will become. And usually the material used for the capillary column is a fused silica. So fused silica, it's so that I don't know if you can see the, if is it too small to see? Maybe I need to stop the share the slide and show this view silica kana.
Yeah.
Okay. So now it's my video bigger now. I don't know.
Yeah.
Okay. Anyway, I bring two types of this is the empty type, yeah. So so this one is empty. I don't know if you can see the difference of the colors. The top is the empty column. The lower one is the monolith color, is a field column, yeah. Maybe you can see the different color. I don't know if you can see the different color. So usually this is a fused silica, because it's like a, you know, it's like a glass, and it's this coating, the color, actually the original column is like this, yeah. It shouldn't be, there's no color, yeah. But to make it strong, because this part, if there's no no coating, it will be so weak, yeah. You can just break the column, you see. We can just break the column, yeah. So this part is the polyimide. Polyimide is the coating. That's why the color looks like orange color, yeah. So why I say it is weak is because this column, don't worry, this column is already used, so I just use it for demonstration, yeah. So for example, this is a normal cutter, yeah. Usually it's very strong, you know. You can turn and it will not break, yeah. But for example, if just something like this, you just touch somewhere, and if you just touch somewhere, it will break like this, you know.
Oh, wow.
So that means when you handle your column, when there's a metal somewhere, you just touch, simply just touch like this, the whole thing will break, yeah. I don't know if you can see, yeah. So meaning that
yeah.
usually it's very strong. Yeah, usually it's very strong. You cannot break. You know, you cannot break. But if there's one scar, we call it like a scar, then it will break. Yeah. So the coating usually when this for GC we just connect the column to the column, but for LC sometimes we have to use this column for the detector, so we can just like cut the coating. Yeah, you can just cut the coating and they will become transparent. Yeah, so it's, I don't know if you can see that you can see the coating is very easy to get. Then you can have the transparent column. Sorry, because I'm rushing, that's why it's become break. Yeah. So usually another thing we can do to clear this coating is to burn with the lighter. Yeah. So we just burn with the lighter and then we just use the methanol to clean, and then we can have a transparent column. Yeah. So this is just an example of the column. But in GC, this is the one that we use. And if you look at the size, of course, it's very small. And if you look at the length here, can you guess how many meter this one is?
5 meters maybe.
Yes, meters. So this one is 25 meters. Yeah. So usually we connect this part. So this is the connector. Yeah. So we will connect this one to the injector, and this one will go to the detector. Yeah. So this is one set of the column. So the connections, it's maybe this one is easier to see. Oh. So the connection, this is the connector. Yeah. So it's the same connector. So, but we have to change the interface. So the ferrule, we call it the connector, we call it the ferrule. So for PET column and for capillary, the ferrule size is different. So we just change the ferrule, and then we have as long as the gas do not leak, any size of ferrule is okay. Yeah? But of course, it has to be fit to the injector and to the detector. Yeah? So usually there will be a holder. Yeah. So this is the holder. We will hold the column, and then we'll connect, and then the column will be hanging inside the oven. Yeah. So this is how we do the column. Yeah. Maybe this is easy. This is the whole thing here. This is the column oven. Yeah. Okay. Sorry. Okay, that's all for demonstration. I will continue. But yeah, anyway. Okay. So the coating here can be different coating, and the diameter of the column can be 0.1, 0.25, 0.22, 0.53. This is the size of the fused silica. Yeah? The one that I show with the monoliths, this one is 0.32, but you cannot see the difference because it's so small. But anyway, for GC, compared to 0.1, usually we use 0.25. Yeah. So the one that I have is 0.25. Yeah. And then you can see sometimes some people use more than 100, more than 50 meters. Yeah. But usually 25, 30 is the common one. Yeah. The one that I have here is 25 meters. Yeah. So the material is fused silica, like I showed you before, and the liquid phase. Liquid phase means the coating here. It depends on the material. Usually it's polysiloxane, yeah? Polysiloxanes, or the like polyethylene glycol sometimes, like a wax. Yeah. So polysiloxanes, it's no polarity, yeah? But polyethylene glycol is a high polarity. Yeah? So depending on your column, but for this one, it just silica. Yeah? So just a silano base. So it's just silica. So it's for it's usually for like polar compounds. Yeah? Okay. So well, Okay, so this one shows the difference between the PEG and the capillary columns. So of course, the PEG column will have a broader peaks like this and with low detection sensitivity. By using a capillary, well, you can see the size is so different and the length is so different. So of course, by using capillary, the peak will be sharp. And when the peak is sharp, that means we can achieve higher detection sensitivity. Yeah? So comparing to the noise. So, and yeah, the noise is also very important in GC because most of the time, if your carrier gas is not stable, you have a lot of noise. Yeah? Like the noise happen and sometimes you cannot get a stable baseline. Yeah? So this one also, it's related to the purity of your carrier gas. Yeah? So if your carrier gas have a low purity, sometimes the noise is very bad. Yeah. So in this case, usually some people will put like we call it molecular sieve. Molecular sieve is like something like a particles. We can absorb the water. We can absorb the like other hydrocarbons of the carrier gas so that we can reduce the noise. Yeah. But most of the time now, if you buy a good GC, it's already in the package. And most of the company, they will tell you, please use purity 99.99% and above. Yeah. So yeah, so you have to use very high purity gas. That's why not many lab can have a GC, yeah, because the requirement for GC is too much than the LC. Yeah. LC is so easy, but GC you need to get the gas. So then usually you have to get a Bombay, and then you have to because it usually come in the high pressure tube, right? So then you have to buy a pressure regulator. So you have to have one regulator at the Bombay, and then you have the secondary regulator as the detector, and then the cost is more. Yeah. That's why most of the lab, they do not have a GC. So it is easier to send the sample for analysis rather than doing it by yourself. Yeah. That's why in my lab, I only have one GC and it's very old. I don't buy a new GC. Yeah. So sometimes I don't use it now. Most of the time we just use LC and LC means only capillary system. So, sorry. So capillary column also, beside the sensitivity, when the separation is better, it also means you can separate in a shorter analysis time. Yeah? So just now there was a questions about how the gas is being separated. So this is one of the example, like drugs in like ketamine, ketamine, cocaine, heroin. So all of these they are volatile. Yeah? So that means they are all small molecules. Molecules, of course, not more than 1,000. So the detector here is GC mass. GC mass is the easiest. It's expensive, but it is usually for the lab, crime lab, or even in the, I think, in the environmental agency of even in Indonesia, right? Most of the time when you want to analyze pesticide or the environmental hormone, or sometimes drugs like this, and usually it's GC, yeah? Because they are small molecules. Small molecules usually are more dangerous. Yeah? So this is one of the example. You can see the peak is so sharp in GC, yeah? Because they use temperature 170 until 200. And if you look at the carrier gas, this is hydrogen. Yeah? Hydrogen is dangerous, but it is the speed is faster. And another thing is, if you look at the column here, is 40 meters. Yeah, so this is so long. Yeah? So it's 40 meters, and then with oven temperature 60, hold up time. This is the temperature. Yeah. So And so usually what we look at when we look at a chromatogram like this, usually we'll look at what carrier gas they use, and then how long is the column, and then the next one we will look is the detector. Yeah. So now the detector here is a mass spec with a scan mode. Scan mode empathy means usually we have to decide the mass with the charge. Yeah? So how much ionization on the mass spec will depends on the which molecule they will cut the fragment. Yeah? So meaning that in the GC, the detections is detection based on the fragmentations of the ions. Yeah? It's not as a whole molecule. Yeah? So sometimes when you use a different M/Z ratio, you will have a different fragmentations. Yeah? I don't know if you have another class called instrumental. Maybe you have another class called instrumental analysis. So in instrumental analysis, usually they will explain a bit about the mass spectrometry. So in the mass spectrometry, there are different ionization method. So the most common one is ESI, electron spray ionization. So, or you can see another one is a chemical ionization. Yeah? So you use the different, well, if I explain this, I cannot finish. Yeah? Maybe I don't explain this one. But anyway, this is one of the typical of the drugs analysis. And this is the example. Yeah. So maybe you know some of the name, heroin, cocaine, ketamine, MDMA. So, some, yeah, not the drugs that we want to take. Yeah. But anyway, the next slide, I will show about what elements that affect the separations. Yeah. So, of course, the column length and the coating, the carrier gas, inner diameter. And as I said, different from liquid, we cannot change the gas composition. So the only thing we can change is the linear velocity of the gas and also the temperature of the oven. Yeah. So when we have usually, if you look at the analysis here, we don't use one temperature. We use multiple temperature. We call it gradient. Yeah? Gradient means like, if you look at here, hold 0.4 minutes, meaning that from 0 until 0.4 minutes, the temperature is 60. Then after 0.4, it will change linear, like 40 degree per minute until 170, and then hold for another 2 minutes or something like that. Yeah. So this temperature program, it's quite difficult to get. Yeah. So when you have this separation is so good, but I think maybe because they already optimized. But in some case, sometimes some people want to reduce the time here. Yeah. But for me, this is already good enough. Yeah. So how the temperature can affect, if you look at here. So isotherm means only one single temperature. Yeah. So for example here, when you have one single temperature, the separations, we have to adjust to the sample that have low retention. Yeah. Because when if we adjust to the high retention, this sample 1, 2, 3, 4 cannot be separated. Yeah. So when we want to adjust to this 1, 2, 3, 4, then sometimes the long retention sample, we have very long analysis time. For example, this is like 50 minutes. Yeah. So when you use a temperature program, you can adjust the time here to make it like this. Yeah. So 1, 2, 3, 4, 5, 6, 7. Yeah? If you look at the time here, this is from 0 to 50, and this is from 0 to 8. Yeah. So less than 10 minutes, you can separate. Another thing is, you can see the sensitivity is also increasing, because the longer time, your diffusion is longer, your peak will become flat, and then your sensitivity will become low. Yeah. So meaning that the program temperature the temperature program not only reduce the time, but also increase the sensitivity. So there are other examples, like we call it technical notes from the Agilent. Agilent, like I said, is a world famous brand for GC. If you look at the library of Agilent, they have a lot of different chromatogram for different analysis. Yeah, it's like a library. Yeah, so you can look at the standard separations chromatogram from Agilent's website. So another company that it's quite famous also now is called the Restec here. So Restec, they also have some good library for you to see. So I found this is easy to understand. Yeah. So if you look, this is isothermia. So for example, when the temperature increases like this, you will see the retention is the same like you reduce the liquid's composition. Yeah. So meaning that comparing to the liquid, we just change the temperature. You can have a different kind of separation efficiency, and you can have a different type of separation time. Yeah. So usually in any GC now, usually you can do the program. Yeah. I mean, you can use the temperature program like this. Hold up how many minutes you hold, from how many minutes to how many minutes you use this temperature, and then you do the program until how many minutes you change the program. Yeah. So anyway, they have a good comparison between the hydrogen gas and the helium gas. Yeah. So helium gas is it's usually it's more popular, but because I heard the productions of helium is less now due to the world market supply. So many people, they will try to switch to hydrogen. Yeah? So their Restec also have a lot of separations. This is one of the, it's like a PDF file. So if you look at the impact of GC parameters, they have a different they have a different parameters, and then will affect the separation. Yeah? So this is one of the effect from the temperature. Yeah? So I think last time when Abu Fitri also give you the textbook of Gary, so you can read more details under the detections of GC and GC mass in Gary textbook. They have more details. Yeah. So another elements you need to consider is, of course, the column. So the column, like I say, it's open tubular. Usually it's 0.25. Yeah. So we don't use to, it's about 0.2. Yeah. If too small, then the coating will be less. If the coating is less, sometimes the diffusion will be, the velocity will be too fast. It cannot control the separations. Yeah. So the solid phase means the type and the thickness. The thickness here, usually the popular ones is the silicon. The non-polar type. You can use different temperature. Usually the temperature we don't use so much to minus. Usually it's between 40 to like until 300. Yeah, not more than 350. Usually just 40 until 200 and then finish. Yeah, and then because this the fused silica, the coating will melt after 400. Yeah, so we cannot use more than 400. So that's why even though the capillary is popular, but sometimes when you want to use high molecular with a higher boiling point, we need to use the stainless steel. Yeah? Because the stainless steel can stand much higher temperature. Yeah? So, and there are many types of the column, the coating. One thing you need to pay attention is the polarity. Yeah? So methyl silicon, when it's just methyl, yeah, methyl, just CH2, CH2, yeah. So with it's a non-polar, and then another one which is popular now is the ethylene glycol, polyethylene glycol, because it's like a wax. It normally is called carbovax. Yeah. So this is strongly polar. Yeah? So in between, it's maybe easier to use depending on your samples. Like for perfumes, something which is more volatile. Yeah. Like petroleum, it already has a smell, and perfumes and aromatic compounds. Usually, we have to use weak polar or weak to moderate. Yeah. And for PCB, I mean, yeah, depending on your compounds also, then we have to choose different types of columns. But usually the coating, the thickness of the coating, it's usually like 0 point something. Yeah. So when your column size is, 0.25 mm, the coating will be like how many microns. Yeah. So it depending on the coating materials as well. Okay, I don't know what I have. So folio, cyano, phenol. Anyway, okay. So if I go back to this actually the coating of the column, if you can get a thin coating, actually it is better than the thick coating. Yeah? Because it will be faster, and then you don't have to waste more time. But of course, if you have a shorter column, then maybe you want to coat a bit more. But sometimes it will cause longer analysis time. Yeah? Because when the coating is more, the gas diffusion will be longer, and then that's why sometimes your separation will not be so good. Yeah. So if your separation is enough, if you can use a less thick column, then the thinner the better. Yeah. And then so for the column, I think this is the common one. Yeah. Then the middle one will be depending on specific the specific things. But most of the time, if you just use this non-polar thing or the strongly polar, you can have good separations. Yeah. So usually they will just come with the methyl silicones. Yeah. So it's like a silica. So you can just use it like this. Yeah. So and anyway, polyethylene glycol also, it's easier to coat because it's like a wax. So this is maybe to have a wider analysis application. Okay. The one that I have here is silica gel. Yeah. So silica gel with coating also silica. So it's more on polar compounds with silano base. So silano, when there's a silano, so it's a SiO. So it's a bit polar because there will be a negative charge sometimes. So depending on, but because my detector is only Fid, so I cannot use other columns. So I have to use a polar column to fix with my detector. And usually when we use a polar column with Fid, you can separate and analyze any organic compounds as long as the compound can be volatile. I mean, can have the boiling point of less than 250. So this is usually the temperature that we use is between 40 to 250. And then the gas that we use is nitrogen. So it's the cheapest. Yeah. Well, cheapest, I mean um, affordable. Yeah. Something that affordable. Yeah. Okay. Sorry, maybe I don't know if I talk too fast about the column and the carrier gas. I will, the next, I will go straight to the detector. Maybe I talk too fast, kana? Anyway, I can have more time for questions if you have questions, but I will show you some of the, okay. If you have any questions, please write in the chat box. If not, then I will explain about the detector. So, well, basically in the detector, like I say, the one that I have in my lab is only FID because it's a general purpose. So it can detect any organic compounds other than formaldehyde and formic acid because this one will interfere with the detections. I use the gas is the hydrogen gas. So anyway, if you look at the detection limit, which is the sensitivity, so you can see FID it's already good enough. It's already 0.1 ppm with 0.1 nanogram. Yeah. So, and a more general one, when you want to have formaldehyde or formic acid, something including this one, then you can use the thermal conductivity detector. But of course, carrier gas, it cannot be detected because there is a background there. So anything that doesn't react with the carrier gas, you can detect. Yeah. So this is when you want to do formaldehyde or formic acid, something like that. Yeah. Something involving this kind of compounds. Yeah. And then another one which has a general purpose is we call it the barrier discharge ionization detector. So all this one can detect all compounds other than helium and neon here. But if you look at the sensitivity, it's it's better than the FID here. But of course, it's a bit more expensive. Yeah. So anyway, the details of the detections, you can Google, it's a lot, yeah, on the internet right now. So that's why it's easier to learn more when you have a good internet connections. Even so, you can have, I think in the textbook of Gary also, they have, I'm not sure about the diagram, maybe it's not so good diagram. But if you Google the Shimazu or Agilent, maybe they will have better explanations about the detections, um, the detection mechanism. Yeah, but so yeah, in the textbook they don't mention so much about the mechanism of the detector. Yeah, maybe the detector you can find out from the company, the makers homepage. They will have a better detection explanation. Yeah. If you need to know more about the mechanism of the detections. Yeah. So usually it has to be volatile and then will detect based on the number of carbon and because it's the organic compounds. Yeah. So it's based on the number of carbon and also based on the number of hydrogen also. But usually it's this how you have to compare with the standard. Yeah. So when there's a standard, then you can do the qualitative analysis. Yeah. Then after that, you have to use different concentration to use quantitative analysis. So this kind of, analysis, it's similar to liquid chromatography. So maybe so that I don't know, maybe you will learn more in another class, I guess. Anyway, beside the general purpose detectors, mass spec is of course it's also multi-purpose, but it's very expensive comparing to the usual gas. You also have to have a very high the purity gas also to have these ionizations. Yeah. Another one which is not so not so common, but it's still for specific purpose. We call it for selective and high sensitivity detector. So this is electron capture detector, and one is for this one. This one is to especially for halogen compounds and also metal compounds. Yeah. So and you can see the detection limit is so high. So this is also 0.1 also picogram, and well, meaning that it is selective and also sensitive. Yeah. Another one is a flame. We call it. This one is not FID. Yeah. FI is to ionize. Yeah. This one is using. Well, it's a bit different. Like so that 0.1 nanogram. Especially when you have compounds that have a nitrogen, so it is very difficult. It's almost impossible to detect with the FID. So in this case, usually, yeah, FTD will be used. Yeah. So if a lab do not have a mass spec, usually you can use this one. But I can say now mass spec already covers many things. Yeah? So maybe this kind of detector is not so popular. Yeah? Unless you have to do a lot of analysis in a company, like for a company, yeah, when a company have different analytical requests from the customer, then they will have different detectors. Yeah, but in a normal lab, like a quality control lab, usually just GC-mass, So because it's getting more popular now, and then the price is also getting less expensive. Well, still expensive, but it is less expensive. Yeah. And then another one is we call it the flame photometric detector. So FTD and this is FPD. Yeah. So this one is especially for sulfur compounds and also phosphorus and tin. Yeah. So these are for specific purposes. Sulfur is actually quite difficult, yeah, because the sensitivity is very difficult to get. And then another one just for sulfur, yeah, is called sulfur chemiluminescence detector. So as the name suggests, we are using the luminescence light to do the detections of sulfur. So especially for organic sulfur, maybe it's easier, yeah, but for inorganic sulfur, sometimes it's quite difficult. Well, at the moment, I think the typical separations or the typical the GC analysis of sulfur is sulfur contained in the petroleum. So petroleum can be very tricky, yeah, because the sulfur content in the petroleum will affect the quality of the petroleum. Yeah? So and also, of course, sulfur is not good for the environment and it is under the regulations. So I think in oil analysis, sulfur content is very important. Yeah? And that is why it is easier to use a specific detector rather than mass spec. Yeah? Because mass spec, the ionization sometimes is too sensitive. Yeah? So sometimes when the interface is already contaminated with this kind of compound, especially the metal compound or something like the sulfur, it's very dirty. Yeah, very dirty means when you use your MS with another analysis, you have some background noise. It's like a contamination. Yeah. So usually when you analyze sulfur, you don't want to mix with other detector, yeah, because sulfur it's a very tricky compound. Yeah. And そうだね。So far かな。Another. So だね。Yeah, so anyway, the common one is the FID or the TCD. Yeah? So these two, it's already good enough. It's more common, yeah? General. Sorry, I have a question. Separation of components is important in computing. As you explain, temperature loaded is more better than isotope. Okay, how to get condition of computing for and especially injector column standard ISO general text. So just how to get conditions of chromatography as injector column detector. It's always try and error to get it. So that usually in GC the standard setup, yeah, it depends. Usually if you just want to see general compounds, organic compounds, it's almost fixed. Yeah? So meaning that the column is a capillary column, 25 meter, 0.25 mm. The carrier gas is nitrogen because it's cheaper. And then the detector is FID. Yeah? So because for FID, if you don't need to analyze small compound or something, just general compound with a general detection limit, usual GC just use a capillary column with a coating of polyethylene glycol maybe, then you can analyze more than 80% of many things. Yeah. So permission. What makes increased column flow rate on detection sensitivity? Okay. And so, and then for the optimum condition, usually you have to see the boiling point of your the boiling point of your compound. Yeah? So you have to bring your column oven to a bit higher than the boiling point of your compounds. Yeah? So inside the GC, usually the pressure is the same, yeah, because we don't control the pressure, so it's almost the atmospheric pressure. So in this case, we just control the temperature is the easiest, and then we just used the temperature according to the temperature where all your compounds can be volatile. Yeah? So you can yeah, normally before you do anything, you can look at the database. So usually it's quite common. You just use a standard. Usually a standard program is like from 40 and then you change to just change to 5 minutes to 250, then you can separate mostly everything. So when you have a more close molecular weight with almost the same uh, boiling point. In this case, you have to have another step. Yeah. So it depends on how many steps of program you want to use. Sometimes it's like linear one time and then like this and then one time. So if between for example, if you want to separate 5 compounds and the first 3 compounds is very close, then in this case, you want to use a slow linear. Yeah? And then if your compound 4 and compound 5, the molecular weight is so much bigger and the boiling point is so much higher, then you can go very fast. Yeah? So this is, like I said, so that it's like you are so right. It's very close, like try and error method. Yeah. So, but if you read more and you have more experience and if you can do some reference, because now the database is so many data. Yeah? So you can compare with the database and then you can just get, you can just roughly guess, okay, maybe like this, So you try with 1 step or 2-step programming, then you can do it first. So when, for example, compound 2 or 3 or compound 4 or 5 is too close, then you have to make another step to just separate that compounds. Yeah. So that is usually how we optimize the condition. Yeah. By optimizing the temperature is the easiest. So, and then the flow, the gas, the speed of the gas will be controlled by the pressure. Yeah. So there will be a regulator on the on the on the gas container. Yeah. So how much you put the regulator will depends on the speed of the gas. So usually the speed of the gas, you can adjust the speed of the gas at the exit, yeah, like at the exit. Usually just by experience, sometimes maybe you can just use a small container like a water to look at the bubble, yeah. If you look at the bubble, oh, okay, maybe like this, yeah. Sometimes I just use my face, so just put the column and then the gas to my face, and then when I can feel the air, okay, like this, something like that, yeah. So sometimes it's by experience, yeah. So for the student, usually they don't know so much, so I will ask them to use water and to look at the exit gas bubble. So if the bubble like boop boop boop, then it's okay. Boop boop boop, boop, then it's too fast, yeah. So it depends on the bubbling also. How you control the speed is by uh, controlling the pressure, yeah. But you don't want to do so fast because you don't want to waste your gas, yeah. So we don't do so fast because we want to save some gas. That's why we increase the temperature. It's cheaper, yeah. Sorry, I hope I answered that question. Another question is increasing the skin column flow rate on detection of, yeah. So because the sensitivity usually it's already almost fixed when you use a different detector, yeah. So the more sample you have, the peak will become higher, yeah. But like I say, if the separation time is too long, then the peak will become the diffusion will become very bad, and the peak will become broad, and then it will become less uh less less height. Then the sensitivity will be decreased. Yeah, that's why it's important to have a program so that we can reduce the separation time and also to reduce the peak area. Yeah, so you need to reduce the peak, the broadening, and then by adjusting the temperature is the easiest. Yeah. Yeah, I hope I answer the questions.
Okay, Prof, I wanna ask you,
Yes.
is there any method to reuse again the carrier gas
No,
after
there.
we finish
Yeah, yeah,
the
yeah.
measurement?
So on some, yeah, it's that like I mentioned before, the recycle. Yeah, yeah, yeah. It's but it's usually very difficult to collect the gas. Yeah, yeah. It's quite difficult to collect because the inlet and the outlet, the pressure will be so different. It is so difficult to collect the gas back. Yeah, yeah. Because if you want to do the line back to the inlet, then you have to have a high pressure again, yeah. So at the end of the column, the pressure is usually so low, so it's difficult to collect for gas, yeah. For liquid it's easier, you can collect
Yeah.
somewhere, but for gas it's almost so difficult, yeah.
So after finish the measurement, the gas is waste. Yeah,
Yeah, it is
they're
waste, yeah.
just waste. Okay.
That's why it's, oh yeah, we cannot feel anyway, yeah.
Yeah.
Why? Oh,
That's
this.
why using GZ is more costly than LC.
Yeah,
Yeah.
yeah, it is costly. Yeah, it is costly. Yeah. Oh, okay. Thank you. I have another question. Okay, Ohio. Hi. Adani, how long the lifetime of GC column car? Okay. Well, it's compared to LC, the GC column lifetime is very long. Yeah. Well, I think more than 2000. It's for maybe because I don't use my column so often. Yeah, my column, this one is already more than 15 years. Yeah,
Wow.
I still keep it and I still use it as long as it is still okay. Yeah. So, but usually, if you use higher temperature, your column crack will become faster.
Yeah.
So that's why the temperature also don't use so high, especially when you use capillary. The coating, it's polyimide. The polyimide coating will become bad. So when the coating become bad, the lifetime will be shorter. Yeah? So usually when the GC, you don't change your column for at least, you can keep at least 2-3 years if you do it even if you do it every day. Yeah. But sometimes depending on your temperature, yeah. So, but anyway, column is consumable, yeah. Consumable means you have to change the column from time to time. So it's a bit difficult, yeah, to maintain the GC. Yeah, yeah, that's why. So then, usually, for capillary, so then, you can repair, yeah, if the damage is in the middle. I mean, you can use some connection to do it, yeah. But the connection, no matter how good your connection, yeah, the gas will leak, you know. So that's why when there's a mirror damage in the column, that is the worst case, yeah, because you cannot reuse the column. No matter how good you try to connect, yeah, your gas will leak, you know. So it's very difficult to repair. Yeah. So that's why once the column is broken, then sayonara, you just sayonara, you know, because it's leaking is so bad, yeah. Yeah. LC-MS math, how to make the chromatogram free from noise and easy to read. For LC-MS math, yeah, you know, when a detector, when it is too sensitive, it also means the noise is too much, you know. So because if it's not sensitive, then you cannot see the noise, yeah. So in other words, if you want to reduce the noise, you also have to reduce the amount of the ion fragments, yeah. So for LC-MS, depending on your m per z value, the number of fragments will be different. Yeah. So if you have so many small fragments, the fragments will also cause the noise. Yeah. So that is why to set the correct m per z value, the ratio is also quite difficult. Yeah. And I said, oh, so if you increase the sample speed transfer, will increase column flow rate and detect. Yeah. I mean, theoretically, yes. If you can increase and temperature flow rate, you can do faster separation, and in that case, the peak will be sharp. Yeah. In one case, it is. Yeah. But that is for but if you have high molecular weight, then you have to use a lot of gas. Yeah, this your answer. Yeah, this is the yes. Another thing, some people ask me, GC mask and LC mask, which is more expensive? Yeah.
Yeah.
So which one do you think, GC mask or LC mask?
For what kind of purpose, Prof?
If for example the same LC and same GC with the same detector, yeah, same like ESI detector for the mass spec. So LC with the same mass, GC with the same mass. I mean mass spec spectrometry. Overall, in total, which apparatus is more expensive? Yeah, I got question like that before.
Yeah, of course, GC.
You might think GC is more
Yes,
expensive. Yeah,
GC. GC.
Yeah,
yeah.
yeah, yeah. I guess so.
Actually, the LC is more expensive. Yeah,
Oh,
LC mask is more
why?
expensive. Yeah, because like in the detector, like a mass spectrometer, you have to do ion. Yeah, for the gas, it's already gas. Yeah, so from the gas
Ah,
to the ion, the amount of energy or interface is
yeah,
easier. You know, you
lower.
can just
Yeah.
connect directly. Yeah, but for LC, for liquid to the mass spectrometer,
Yes.
you have to have extra ionization spray or something. Yeah, and the interface is actually very expensive. Yeah? So in terms of in terms of Japanese yen, so GC mass is like 1000万, you know, what is 1000万, or maybe less than now is about 800. So 800万, 8 million yen. 8 million yen is how much? You have to times to how many zero yen? Anyway, for example, a GC mass is like with the same with the ESI detector, for example, is about 8 million yen, but LC mass will be about 20 millions, yeah, something like that. It will be 3 times than the
3 times.
because of the interface. Liquid to change to ion, it's the interface is very difficult. Yeah. Yeah, so that yeah. But anyway, for environmental analysis like pesticide, dioxin, you know, and then PAH, polyaromatic hydrocarbons. Not all the PAH. There are only 15 types, which is it's regulated by the law by EPA. So like, you know, benzoyl A, pyrene, like bisphenol A, something like that. So these kind of things, it's still use GC. Yeah? It's easier to use GC. And another one is, of course, the pesticide and pesticide in food. Yeah. So food additive, pesticide in food, all these are still using GC. Yeah? So you don't need a GC mass. You can just use a GCFID, yeah, to do this analysis. So that for environmental analysis, you still need that. Yeah? LC, it's more like a quality control. Yeah. So quality control in like the active compounds, you know, something like that. Yeah. If you last time, you know, before I want to become a docent, I mean a professor, I wanted to work in the United Nations to be the analyst of like a environmental analyst. Yeah. But at the time when I look at the qualifications, it says able to operate GC. Yeah? They don't say LC, they just need a GC, you know. I said, oh my God. So they don't need LC, they only need GC. At the time, I don't have much experience about GC, so I didn't apply. But after that, you know, my friend who is working in the United Nations, they say the work is so boring because everything you have to follow the protocol, everything you have to follow the fixed method. There's no research, just monitor something like that. So it's quite boring, she said. But anyway, we need somebody to do the quality control of our air. Oh, okay. Okay, thank you. We still have some time for question.
Yeah, by the way, anyway, have you finished your slide?
Oh, yes, I still have one more slide.
Oh.
Okay. Anyway, so, I finished with the selective detector, yeah? So, so this is like the amounts of samples that we can do between the GC mass and LC mass, yeah? So, I mean, in a developed country like Japan or you know, like America, or in the Europe, like Germany, British. So usually, you know, GC mass or GCMM, GC mass and LC mass, mass now, you know, because of the tandem mass. By changing the different mass, you can have different molecular informations. Then you can use the molecular information of the fragment to determine your molecule. Yeah. So if you look at here, GC you can just use for something smaller, small compounds. Yeah, like less polar. Something you can know, like in Indonesia, it's very popular. Yeah, essential oils. Yeah. So essential oils, perfume, terpene, wax, all these are less polar compared to alcimas, which is the application will be more to the polar compounds like organic acid, organic amines and nucleotides, ionic species. But there are some in the middle one, you can use sometimes both depending on the conditions, yeah. So like steroid here, yeah. Steroid will depends on what kind of derivatives, yeah. So when the drugs is different, because now the when the drug, the people who are selling, especially the illegal drug, you know, they will try so much so that your illegal drug cannot be detected, yeah. Yeah, so they are so good so that whatever you do and oh, city asked for the textbook. The textbook that last time Buffy sent to you is already good enough, yeah. But for detectors, if you want to know more details of each detectors, I recommend you to read from the company's website, yeah. Because the company, they want to sell their detector, so they will explain very detailed their detector, yeah. So you can learn more about the detector from the company's homepage, yeah. Like company like Agilent, Shimadzu, Restec, they have a very good library, yeah. I recommend you to read Agilent. Agilent, they have a very, if you look at the textbook that Book Tree sent to you, I mean the PDF file, I think you have the PDF file. You can look under the chapter 20, gas chromatography. And then Gary also give you a link of the library of the link of Agilent, the company's library. You can even Google, it will come out, yeah. So sometimes the detections, you know, like GC mass, LC mass, it's a lot of applications in drugs analysis, yeah. Like, but now illegal drugs is so difficult to detect, yeah, because they will try to use different compounds. They will synthesize the drugs so that you will not be able to separate, yeah. You have to overlap with something else, yeah. So when you detect, there will be a matrix. You cannot see what kind of drugs is there. So now I think usually the drug, the person who sell the illegal drug, they are very good organic synthesis chemists, yeah. So it's so difficult to catch them with a specific drug, yeah. Yeah. Recently, actually last week, I just attended the annual conference of the Japan Chromatographic Society. So every year, this is the first time after the corona, we do on site, yeah, like the offline, you know. So, but it was a hybrid. We have about 70 researcher attend on site, and then about 190 of chromatographers attend online, yeah. So almost more than 50% of the presentations is chiral separations and also LC mass of drugs. Yeah. So it's more on this kind of compounds. Yeah. And most of the people, they are from the pharmaceutical area. Yeah. Pharmaceutical company or from the faculty of pharmaceutical. Yeah. So they want to use more chromatographic method for separations of drugs and so on, and chiral separation also, yeah. One type of the affinity the chromatography, so chiral separations. So most of I think 90% of the presentation is, or maybe 95% is LC, yeah, not GC, yeah. Very less GC, yeah. Yeah. Okay, this is my last slide actually. So the next one is just thank you, yeah. So okay, I don't know if you have other questions.
Sure, I got a question, Prof,
Yes,
about
please.
TCD, yeah, TCD thermal conductivity detector. Yeah.
Yeah.
My question is why is the nitrogen or any other carrier gas cannot be detected in the TCD? Because as far as I know, all gas have thermal conductivity at certain temperature. Is it because the limitation of temperature in GC? Or
One thing is that. Another thing is if if for example, if you use the FID, then we have to use you have to remember the detector also. We have to use a gas in the detector. So sometimes the background will affect the detection and it cannot come out. So yeah, you are right. Yeah, it is. But yeah, for compounds like nitrogen, usually you have to use TCD. It's cannot be detected by other FID, something like that. Yeah, because of the detection. So the thermal. Basically, you can have others as well. Just the sensitivity is not so high. Yeah? So I don't know if maybe I don't answer your questions. Yeah. So yeah, you cannot the noise will be overlapped with something else. The sensitivity might not be enough sometimes. Yeah. So yeah, my experience is sometimes you cannot know which peak is which peak. Yeah. So yeah, and then sometimes there's no peak at all. Yeah. Maybe because the sensitivity is not high enough, and that's why there's no peak. Yeah, sometimes we thought it's the column problem, but sometimes it's the detector's problem as well. And then with the gas we use for the detector also will affect. Mm.
okay, thank you, Prof. Okay, all right. For all participants here, we still have 10 minutes. Maybe you have any question to Professor Lim, please write in the chat box, or you can raise hand and ask directly to him, to her.
There's this question
Oh yeah,
from
Adisti. Adisti.
Adisti.
Yeah.
The liquid phase, we call it liquid phase, is actually the coating itself is like liquid light, yeah. But actually it's part of the coating, yeah. So it's already coated inside the internal face of the column. So then I mean in terms of characteristic, yeah, it's liquid light characteristic. That's why in most of the textbook it is called liquid phase. But when it is dry, it is actually looks like it's like a wax, something sticky, yeah. But it is not really usually, yeah, we call it, yeah, there is a definition, yeah. So we don't, when you have a different pressure and a different temperature, the gas will be liquefied, will become liquid also. Yeah. So yeah, so inside the column, maybe the diffusion will be different, and then it will become like a liquid. The phase, the for the separation will become liquid light. Yeah. So yeah, so depending on the temperature and the pressure, the gas also will be liquefied. Yeah. So yeah, the definition is liquid phase. Yeah, yeah. Even though it's a coating. Yeah. So because when it's come out dry, it's different. If you cut the column and if you see the cross section of the column, then you will know it's like a coating already. Yeah. Mm. But inside the separation, when you have a different pressure and a different temperature, the mobile phase, the gas, I mean the carrier gas will be liquefied at some extent, and it will have interactions with the coating, and it usually called liquid phase.
Okay, is there any question for participants or anything's clear?
Sorry.
Oh, this is from Siti Faika, Professor.
Thank
It's
you.
like you didn't enter that company, otherwise I can hear you. Okay.
But maybe if I enter the that cup, because
Company.
you know, maybe who being a docent, you know, the salary is not so high. So it's the same government. My friend who work in the company, in the first 3 years, their salary already 2 times my salary. So
Wow.
yeah. So usually when we have the class reunion, so my classmate who work in the pharmaceutical company,
Yeah.
company pays the highest salary in Japan.
Yeah.
So every time when we go for we call it nomikai, the party. Well, the first party, everybody will pay the same price. But in the second or third party, when you have a small group, my friend who work in the pharmaceutical, he will pay for everybody. Because his salary is so much higher than our salary.
Yeah, if you enter the company, we will not meet again. We will not meet. Yeah.
Yeah.
You won't teach us.
No. Anyway, okay. That's all for today. Yeah, thank you for your
Yeah.
kind attention.
Okay. Well, thank you so much for Professor Lim for an excellent explanation for us about GC. Yeah, and also we were also equipped by column demonstration. Yeah, so I believe students and all participants here can have an imagination about what they have
Maybe.
learned so far about column.
Yeah, and this is a syringe we use here.
Yeah.
It looks
Thank
so
you.
scary, because sometimes it's
Yeah.
quite scary.
Yeah.
The worst thing is when you want to pack the column and you do like this and you drop your syringe. Sometimes the student drop, and if you poke on your legs, it's really painful. So
Yeah.
but for me, painful is one thing. For me, I don't want my student to break the needle because it's expensive. So when I
Okay.
drop my syringe, the first thing I will check whether it is broken or not. Uh, so
Yeah, if it will be broken, you will be get angry, right? As a
yeah, but usually
supervisor.
now we don't really use the GC anyway. Okay.
Okay, and also thank you for all participants here who has joined us in the today's meeting. For reminder, the schedule replacement only for this meeting. So the
Yeah.
next meeting will be back to the original schedule, Tuesday, 1 p.m. Indonesian time. And
Right.
don't forget,
Right.
also, we have a webinar, which is collaborated with Indonesia Chemical Association on Tuesday, 14 December. The speaker is Professor Lim and also Dr. Muhammad Rafi from IPB. The webinar entitled "The Current Application of Chromatography." Yeah, and it will be so interesting and full of knowledge shared by the expert. Again, don't be forget to register. Last, I will say thank you for everyone here. I will close this and see you next week. Bye bye. Thank you so much, everyone.
Same to you. Have a great day.
Yeah, have a good
Halo,
day
Prof.
too,
Lim.
bro.
Bye. Jangan.
Okay.
Hai,